If the electrons flowing in a circuit move backwards and forwards about a mean position, then the current produced is known as alternating current, or AC. In this lesson, we will review the operation of a simple alternator or AC generator. We will look at the advantages that AC systems have over DC systems, and we will explain the terminology that you need to become familiar with when discussing AC systems. A simple AC generator consists of a loop of wire or an armature rotating in a magnetic field. We will take a look at the simple generator as the armature rotates through 360 degrees to see what sort of voltage is produced. In the position shown here, the coil will initially be moving in parallel with the magnetic field, with a phase angle of 0 degrees, so no EMF will be induced. As the coil continues to rotate, it begins cutting the field at a small but increasing angle, and an EMF begins to be induced. As the coil approaches 90 degrees to the direction of the magnetic field, the maximum number of lines of flux are being intersected, and the EMF is at its maximum. Between 90 and 180 degrees, the number of lines of flux being cut by the coil reduces again, so the EMF reduces, until at the 180 degree point, the coil is again moving in parallel with the magnetic field, so no EMF is being induced. As the coil moves around from the 180 degree point, it once again begins cutting through the field lines, but now in the opposite direction, so an increasing EMF is induced with an opposite polarity, until at the 270 degree point, the coil is cutting through the maximum number of flux lines, and the negative EMF is at a maximum. The EMF now begins to fall again until the circle is completed. The coil is again moving parallel to the field, the EMF is 0, and the cycle begins again. The alternating voltage produced by this type of generator is known as a sine wave or a sinusoidal output. A sine wave can be given an angular notation called phase. One cycle represents from 0 to 360 degrees of phase. The current flowing in the external circuit will be an alternating current, or AC. That is to say, the current will first flow one way, then change direction and flow the opposite way as the polarity of the induced EMF changes. There are several terms used to describe alternating current, and you need to become familiar with these terms. As shown on the graph, a cycle is one complete series of values. A cycle can be split into two halves, known as a positive half cycle and a negative half cycle. We have already mentioned phase angle or phase, and we know that one cycle represents from 0 to 360 degrees of phase. The number of cycles occurring in each second is the frequency of an alternating current. The unit of frequency is the hertz. 1 cycle per second is equal to 1 hertz. Aircraft constant frequency AC supply systems usually have a frequency of 400 hertz. The period is the time it takes for one cycle to occur. It is the reciprocal of the frequency. The period in seconds equals 1 over the frequency. The amplitude or peak value is the maximum value attained in one cycle. Alternating current, or AC electrical power, has a number of advantages over direct current or DC. Some of these advantages are self-evident, but others will become clear as you move further into the subject. AC generators are simpler and more robust in construction than DC machines, because they do not have commutators, and only the light current field coil is rotating. Because they don't have commutators, AC generators do not suffer from the problems of arcing at the commutator associated with DC machines, and consequently are more reliable, especially at high altitude. They also require less maintenance. An AC generator can be significantly lighter than a DC generator, with the same power output. Because the rotating elements are much lighter, AC generators can be operated at much higher rotational speeds than DC generators, so they can produce a much higher voltage output. Three-phase AC motors, which again do not require commutators, are simpler, more robust, and more efficient than DC motors. Again, AC motors are fully explained in a future lesson. The supply voltage can be converted to a higher or lower value with almost 100% efficiency using transformers. Any required DC voltage can be obtained simply and efficiently using transformer rectifier units, or TRUs. Transformers and TRUs are fully explained in future lessons. AC generators operate at much higher voltages than DC machines, so for the same amount of power, the current required is proportionally less. This means that considerably thinner and lighter cables can be used than is possible in DC systems. Spend a moment studying the list on the screen before moving on. Because they don't need commutators, practical AC generators normally have the positions of the field and the armature transposed from the positions used in DC generators. That is to say, the field is on the rotating assembly, and the high-power armature windings are stationary, in the same way that they are on a DC alternator, but without the rectifier. The field may have more than one pair of magnetic poles. Shown here is a generator with 3 pairs of poles. Aircraft AC generators normally have 6 or 8 poles. A cycle is completed each time a north and a south pole of the magnetic field move past the armature. Thus the frequency of an AC generator is the number of times a north and a south pole pass the armature in 1 second. The formula for calculating the frequency in hertz of an AC generator is shown on the screen. For example, a 6-pole generator rotating at 8,000 RPM will have an output frequency of 6 divided by 2 multiplied by 8,000 divided by 60, which is 400 Hertz. We can see from this that the frequency of an AC generator is dependent on the rotational speed of the rotor and the number of poles in the field. The effective value of an alternating current is calculated by comparing it with direct current. The comparison is based on the amount of heat produced by each current under identical conditions. An AC current with a peak value of 10 amps will be constantly varying between 0 and 10 amps. So a steady DC current of 10 amps will make a resistor hotter than will the AC current with a peak of 10 amps. To make the resistor as hot with an AC current, its peak value must be higher, so that its mean value can be 10 amps. This mean value is termed the root mean square, or RMS value. As the current or voltage rises from 0 to maximum in 90 degrees of phase angle, the mean value will occur at the midway point of 45 degrees. As the values follow a sine curve, then the value at 45 degrees can be calculated using the formula sine equals opposite divided by hypotenuse. In our case, the hypotenuse is equal to the peak value, and the opposite is equal to the mean value. The sine of 45 degrees is 0.707. So in our case, 0.707 equals the mean value divided by the peak value. By transforming the formula, we can say that the mean or RMS value of alternating current or voltage with a sinusoidal waveform is given by the formula RMS equals 0.707 multiplied by the peak value. In our earlier example, the AC with a peak value of 10 amps has an RMS value of 10 multiplied by 0.707, or 7.07 amps, which explains why it produces less heat than the 10 amp DC current. Most AC supply values are given in RMS terms. Ammeters and voltmeters measuring AC are normally calibrated in RMS values. Aircraft AC generators normally operate at an RMS voltage of 115 volts. Watt to the nearest volt will be the peak voltage. Type your answer in the box and click on Enter. That is the end of the lesson. You now know the advantages that AC electrical systems have over DC systems. They are being displayed on the screen. Spend a moment reviewing them before moving on. You now know the terms that are used when describing alternating current. They are being displayed on the screen for you to review. Finally, you can calculate the output frequency of an AC generator using the formula shown.